today is about um, kinds of things that when standing still don't like to stand up. They'll fall down, um, and but they can also balance when they're moving. Um, and so I think that little GIF was sort of a nice metaphor for the um, the evolution of things that I studied and trying to think about the stability of walking, which motivated all this work. Um, so walking is rolling is walking. So uh, let's go to the next slide. I just thought I'd point out real briefly where I'm from and where I'm talking to you from. I live in Burlington, Vermont, right on Lake Champlain in New England. And in the building I'm giving the talk from, this is a picture I took last night from our the terrace on the top floor of our building, looking directly west across Lake Champlain at the Adirondack Mountains in New York State. So it's a beautiful place to live. Right now, when I woke up this morning, the temperature was about 50 degrees, and it'll get maybe up to 70 today. So it's a good place to be in the summer. Here's the outline for my talk. Start off with some preliminaries. All of this that I'm talking about today, about things that can't balance while standing still, but like to balance while moving, started with an interest in two-legged walking that formed the basis for my PhD research. But we'll take a step back from talking about walking and just talking about things in general, some common examples of things that fit into this category. Then I'll give some more introduction and background to the theme questions that drove the research that I did, which includes some motivation for why we thought we could do what we wanted to do and some of the history, and then talk about my specific research question and goals that I had. Then I'll talk more specifically about the research program and the methods that I used in my work, an evolution of models to build up our muscles, so to speak, with understanding how to study legged walking systems. That will involve talking about dynamical modeling, numerical simulation, stability analysis, and how we search through parameter space to find stable walking motions for these variety of systems. And specifically, I'll talk about three things. A monocycle, which is a one-wheeled vehicle, which is a rider inside a wheel. The rimless spoked wheel, which is a really simple analogy to legged walking, and a good place to start with trying to understand the features of legged locomotion. And then I'll go to finish up with two-legged walking. So as I said, this all starts with two-legged walking. If you take a human being and you remove their brain and their muscles, the nervous system, and you let them try to stand still, they'll just fall into a heap in the floor. Right? So pretty spectacularly, a human being without those key things will just fall over. But a human being with all the parts in place can stand still and walk, balancing in both cases, when without the brain and muscles would like to fall over. I found this nice animation of from Edward Muybridge's photography from the late 1800s. So what are some examples of things that can balance while moving but can't stand still? And what are the kind of things that contribute to their ability to do that? So there's a spinning top. There's a bicycle wheel, the bicycle itself, and a rigid rider and a skateboard. They're all examples of things that can, that if you try to let them stand still, they just fall over. And if you spin a top or roll a bicycle wheel or shove a bicycle or a rigid rider and a skateboard, they will all manage to balance while moving, but they will spectacularly fall over. So the question is, how do they balance while moving? And we'll come back to that when we look when I look at a few videos of these devices. So what do I mean by uncontrolled? Just to be clear, no computer, no sensors, no feedback control, unpowered, no muscles, no motors. So and the things we're looking at, the only things that are driving forces are gravity and forward inertia. And what do I mean by balance? So in all these cases, essentially what each of these devices is an inverted pendulum. When you release it from rest in a perfectly vertical position, if you bump into it, it'll fall over. So we can, this is such a simple system. You're all familiar with it. We can get the equations of motion, linearize them, and you get the familiar equation for an inverted pendulum, displaced from the vertical by an angle theta. And when you solve those linearized equations for small angles, you get exponential growth. So you push this over, the angle will increase, and the more that it falls over, the greater the torque due to gravity, and it will fall faster and faster. So all of these things, inverted pendula, they have this exponential instability. So what I mean by balance is exponential stability. Somehow these systems that when you just release from rest want to fall over, there are ways to balance these things while they're moving. So how do you balance these inverted pendulum objects? You move the support point under the center of mass. You move it to be under the center of mass, or move the center of mass to be over the support point. So passively, how can you do this? One way to do it is with a big curved foot, and the other is to add torsional springs and dampers. So this is what inverted pendulum might look like if you add a big curved foot to it. And if the center of curvature of the foot is greater than the location of center of mass, this will just rock back and forth about the on the base and balance. Another way to do it, of course, is to add torsional springs and dampers. And again, if you write the equations of motion, you get this familiar spring mass damper system that if you have the stiffness big enough compared to gravity and a positive damping, you'll get decaying oscillations. And the pendulum will return to the vertical position when disturbed from that position. So I've boxed those damping terms, the stiffness terms. I want you to remember those because there's a way to get those in these systems that we're going to look at that don't come from actually adding stiffness and damping to a system. They come from things like coupling of lean to steer with various kinematic constraints or special mass distributions. So you can also balance these things actively with control. So I found this a video of the longest duration to balance a stick on an index finger of the hand. And so you can see the person here just balancing the stick by moving their hand when observing it falling left or right. You can also do it with sensors and actuators. And I found this work by a professor from Greece, and I'm sure you've all seen systems like this. So we'll just take a quick look at this. So this is the kind of thing that the kind of work that I didn't do myself. It's not in my bag of tricks to be able to design and build systems like this with actuators and sensors and um, software packages all put together. Anyway, so this is the way you can do it actively with control to balance this stick that would like to fall over. And what we're focusing on is not doing that. So what are some things that can help balance these statically unstable objects um, while they're rolling, spinning, or doing other motions on the plane acted on by gravity? Having fast spinning or parts or fast rolling, fast enough. Special kinematic constraints. So pure rolling without slip, with point contact, um, um, which leads to coupling between various kinematic degrees of freedom. Uh, Energy dissipation can kill disturbances that you can have in systems due to collisions and or friction. Various kinds of deformations, springs or inelastic deformation. And as I'm especially going to focus on is special mass distributions and various mechanisms, linkages, which can couple internal degrees of freedom in a system, like the two parts that make up the bicycle steering, body segments in a robot or um, a human body. So spinning tops, if you spin them fast enough, I got this top this week, and it's a really nice one. It lights up. If it spins fast enough, the as it starts to fall over and want to fall over due to gravity wanting to knock it over, when the center of mass gets left or right of the contact point, the rate of change of angular momentum counterbalances the torque due to gravity, and it can stand in place. Bicycle wheels or rolling coins or rolling discs. These videos were made. This is Steve Collins. Andy Ruin, I believe, is doing the video. You can see how it rolls pretty much in a straight line. You can whack it and it will right itself. So there's a wobble in the lean and the heading due to disturbance, but it dies out if you're rolling fast enough. That's due to frictional dissipation and this non-holonomic pure rolling constraint. If you look in the ideal case without friction, at best, rolling discs can be neutrally stable. When you disturb them, they wobble forever at a slightly different heading. So they're not technically stable, but they will stay up if rolling fast enough without friction. Bicycles are also self-stable without a rider, without someone steering it. Again, it has this lean to steer coupling, pure rolling constraints, just the right mass distribution. You have to be going fast enough, but not too fast. But as it turns out, in theory, anyway, the balance of bicycles is not dependent on dissipation, gyroscopic effects, or trail in the steering, the caster effect, all things that are commonly thought to be necessary for bikes to have self-stability. Okay, so those were the preliminaries that I wanted to cover, just to get to lead us into the research on walking, which is where this all started. So again, walking on two legs it's really efficient. Doesn't require a lot of energy. We balance really well in all sorts of complicated situations. We don't fall over. It's basically easy. I found this quote in this lovely book on the movement of animals. It was written in 1681, so before Newton, uh, um, talking about the physics of animal locomotion. And so people have been thinking about this for a long time. So why is this so? Why is walking, why does it have these appealing features? Um, so walking on two legs is simple, but it's also really complicated. So how does it work? Uh, Clearly, there's the biology and there's mechanics. So in physiology of locomotion, there's this interaction between the muscles, the brain, and central nervous system, and all the sensory systems involved. So they're clearly part of controlling and powering stable, efficient, and dexterous walking over complicated terrain. Um, there's also the interaction between the pure mechanics features, which is gravity acting on animals that walk. There's forward inertia. There's this collection of bodies that are connected by various kinds of hinges, and then there are these dissipative collisions with the feet with the ground and in the joints. Um, so both of these things contribute to uh, how walking works, and um, so this so biomechanics is necessary to understand and completely how walking works. Um, but the question you can ask is how much, to what degree do each of these things contribute, and what might be learned from that? Asking that question. So clearly both are involved, um, but to what extent do uh, the the biology and the pure mechanics itself play a role in the stability of two-legged locomotion? I wasn't looking at other things other than stability. I wasn't looking in particular at efficiency or the dexterity of animal locomotion, just basic stability. Um, so one approach is to um, make the assumption that the brain and the muscles are heavily involved. Start with lots of control and actuation and optimize for efficiency and stability. And so you can ask this question. But another approach is, what if you just remove all those things and see what pure mechanics all by itself, just looking at the role of inertia, forces from the environment, interactions with the environment, um, and how the mass is distributed, how these things are, how there are multi uh, bodies connected together. So start with a passive system and then optimize for stability and efficiency, and then perhaps later add actuation and control for more complicated walking. So why might you take this passive dynamic approach? Um, Perhaps understanding the underlying dynamics of how walking on two legs works, understanding it better. If your aim is to build biped robots, why might you do that? Well, sometimes it's better to have robots walking around and doing things that are dangerous for humans. You also might want to uh, be able to design and produce more effective prosthetic devices and other solutions for walking problems. So perhaps it's easier than starting with a complicated control system. It's an open question. We were always wrestling with this in the lab. Andy Rowena still talks about it in his recent talks about how is it that what's the best approach for designing these systems that um, uh, need to be efficient and stable. Um, um, because it's not clear that one approach is best. So some hybrid approach is um, desirable, perhaps. But I focused on pure mechanics and stability of walking, and in particular in 3 dimensions. So, what makes it, why does this approach make sense? Why does it seem like a reasonable way to approach studying this problem? If you look back at airplanes, um, they started with pilotless gliders. So there, and then those evolved or um, into powered and piloted airplanes. So the Wright brothers, Lilienthal, Chanute, back around the turn of the last century, started with these gliders that could fly quite well, but without any control or power. Humans and animals, if you look at how much neuromuscular activity there is in normal walking, it's you can investigate this by looking at things like looking at muscle activity with EMG, and very little is required to keep walking and to keep upright. There have been these walking toys around forever. Gravity-powered walking toys do exist, and they can walk with a kind of gait, but then most in all cases can stand still. So they violate this rule that that if you try to stand them up, they won't fall over, they'll stand still. And it would seem that if you're starting from there, that it's easier to walk if you have the ability to stand up, and all these toys happens with large feet. And then there are these 3D devices that we've been talking about: bicycle, a rider, and a skateboard, and a spinning top, and they all are some evidence of this passive ability to balance without outside interference. And lastly, and I put this to emphasize this, there was the work by the great Tad McGeer in studying, analyzing, modeling what he called his passive dynamic walking robots. There were 2D devices constrained to walk in a plane that he worked on from 1987 to 93. The work was just spectacular. So here, just to show you, here's some of these walking toys. And so they have these really simple gaits, but they can walk with a steady gait without anything controlling them to take a certain step size or to wobble in a certain way. It's just the natural dynamics that falls out of their behavior and their design. So here's Tad McGeer's amazing need passive dynamic walker. I put the second video up here because I just wanted to illustrate how all the ways that these things can fall down, but yet with the proper design and the right initial conditions, it can walk quite well and quite human-like. So these devices are powered only by gravity. They are constrained, as you can see, with 4 legs side by side to walk in a plane, so there's no lateral stability problem. There's no motors, no control, no gyroscopic effects from fast spinning parts that keep it up. It can't stand still with feet together, but it can stand if you spread the legs apart. It has apparently stable, steady gaits, and that was corroborated by models, computer models. But still, even with computer modeling saying these things should be able to work, there was a tremendous amount of tinkering that needed to go on. There are these special dampers at the knees that were required, that something that didn't come out of modeling, but that came out of observation. So what were his goals? Build a passive dynamic robot with a stable gait. As I said, he did this, he built mathematical models, did computer simulations, and built these physical models. The only power was gravity down a shallow slope. It was okay. The rules of the game included being able to add springs, dampers, any kind of multiple bodies could be arms or other things if necessary to make it work. And these various joints and so on were allowed. And he had an aim towards making powered, controlled robots, but the idea was to add small amounts of actuation and control once you've got a passive dynamic walking robot. So he was successful with these 2D walkers. He tried to do the same in 3D, but he was unsuccessful. He started with modeling, but he never got to building and trying to test out walkers that could walk passively and stably in 3 dimensions. And that's where that formed the focus for my thesis, was to see if we could do that. And the aim was to do it all with the computer. We didn't have any aim of getting to the point where we would build it. So that's where it all started. Okay, so what was my specific set of goals and questions that I was looking at? Same thing that McGear was trying to do, but free to move in 3 dimensions, with the same constraints on the same things tying our hands that were the rules of the game that McGear was following, and see what kind of features were necessary to see for passive, stable walking gaits in 3 dimensions. We got a Whitaker Foundation grant to answer exactly the set of questions. So I like to draw, if you didn't notice. All the sketches in here were ones that I made. Just trying to illustrate what it is we were trying to do. Can Newton alone pull the strings, allow that skeleton that I showed earlier, be able to walk if you add only things like passive elements like special mass distributions, putting masses in special places on it, perhaps dampers and springs and so on also. So the key thing was, here again, just to reiterate, are these list of rules that we were playing by. The key thing that I focused on were just 3 things: special mass distributions, the dimensions of the various parts, and the number of links and joints, and possibly adding springs, dampers, and frictional devices as necessary. One thing I really want to focus on is mass distribution. The idea is that in systems, if you add crooked mass distributions, and I'll explain this, what I mean by this in the next couple of slides. As these inverted pendulum devices start to fall, if they have crooked mass distributions, meaning they have asymmetric mass distributions, twisting motions can be induced because the off-diagonal terms in the moment matrices for these bodies can induce twisting motions. And that, in addition to special rolling constraints and other kinds of kinematic constraints, can help push the center of mass back over the support point, same way it does with the lean to steer coupling in bicycles and so on. So here is, I wanted to illustrate this with an example. So imagine a symmetric dumbbell that's rigidly attached to a rod supported by a ball joint, and then an asymmetrically distributed dumbbell with respect to the vertical support. So it's all one. Each of these is a rigid system, but can be released from a small angle about the x-axis. Now, if you look at the one on the left of the symmetric dumbbell, it will just fall over, straight over, with an angular acceleration only about the x-axis. But because of those product of inertia terms in the moment of inertia matrix for the second case, as it starts to fall, you will get an acceleration about the x and about the z axis, and it will curve as it's falling down. That feature can contribute to stabilizing some of the systems that I studied, and we'll see how that. And as it turns out, for the case of the monocycle, that's exactly what can allow a wheel with a rider inside can balance when uniformly distributed mass disk can't. Here's the approach that we took to building up our understanding of how to study these kind of systems, these smooth systems, which are rolling wheels and so on, and these systems with intermittent dynamics, where smooth motions are interrupted by collisions of feet with the ground and joints in walking systems. So we studied an evolution of these simple mechanical analogs to walking by increasing the complexity of the features. So this family tree diagram shows in the plane in the middle that we start off with these 2D versions, 2D rimless wheel, simple ordinary wheel, simple 2D point foot walker, and then branching out from there and adding capability to move in 3 dimensions on a plane. So today's talk, I'm going to talk about this 3D wheel with crooked masses, which is a simple model for a monocycle. A 3D rimless wheel, which has very simple, simplest aspects of leg and locomotion. And then in the end, I'll talk about these 3D walkers. So why look at rimless spoked wheels? Again, we're trying to build up our understanding of how these things work, these simple walking models in 3 dimensions. And so it has some features of walking, the foot collisions, the rising and falling of the center of mass, the falling and catching aspect of walking. If you can imagine a rimless wheel, rimless spoked wheel, or a rolling polygon, you can imagine that it can have steady gaits and maybe even stable ones rolling downhill in 2 dimensions. And it has that inverted pendulum instability in between collisions of the spoke tips with the ground. Of course, it doesn't have leg oscillations. No, it has fore-aft stability, meaning as soon as there's rotation about a spoke on the ground, the next spoke hits the ground. In 2D, there's no lateral instability. As I said, it's a good first step for learning about these various features of walking. Systems with intermittent dynamics. It's a very simple problem, both analytically and numerically. And when you look at a rimless wheel rolling down a hill, it kind of looks like walking. So here's some interesting rimless wheel devices that I came across in the literature and in the public press. I just thought they were sort of interesting, cute examples. So why look at round wheels and round wheels with crooked masses? This idea of just looking at mass distribution alone and its effect on the dynamics and stability of systems that are 3D, and also without dissipation, um, and with this simple pure rolling constraint, point contact, knife edge, no slip. Um, and this can give us some idea how things can balance without friction, without energy dissipation. Perhaps we could find stability even without gyroscopic effects and without control. So this is just a schematic of what I mean by a disk with crooked masses. And again, it has these off-diagonal terms in the moment of inertia matrix that can lead to a coupling between lean to steer. And as this thing is rolling around in the plane, the massless fork is just a support to keep the crooked masses from rolling with the disk. But both the non-holonomic constraint, as this thing starts to fall over if it's disturbed, can kind of steer it back to being upright, and the mass distribution can add to that feature. So with all of these systems, the rolling disk with crooked masses, the um, rimless spoke wheel, and the simple models for walking, this is the research approach that we took to find a complete mechanical model that has all of the things that you would expect, the necessary kinematics to describe the position and the orientation, material properties for contact, the contact mechanics in terms of the kind of rolling constraints and so on, the collision mechanics. How do you model the collision of feet and spokes with the ground, and all these other features that are important. Then derive full nonlinear sets of equations of motion, find steady or periodic motions, and solutions to the equations, and do a linear stability analysis around steady motions. And then if you don't find, of course, to start stable, steady motions, vary the parameters to find stable, steady behavior. So let's let's start off with monocycles, of the three things. Monocycles have been around since the late 1800s. These really cool vehicles where you sit inside the wheel and the wheel is driven around the rider. These things still exist today, although they're not very popular. But the rider pedals the wheel around himself and then leans to steer and to balance. So the rider heads and banks with the wheel, but doesn't roll with it. Here's some photographs of some monocycles from 1950s, 1970s, and 1990s. Here's some motor-powered versions. And I just had to show you this video here from 1927, showing a powered monocycle. So clearly, when you see the this kid without much effort, clearly probably not very coordinated or whatever, at the right speed, is rolling along quite stably, and it's really fun to watch. So let's just review quickly what we're talking about here with wheels. A real wheel, showing one with like a tire on a rim, a spoked wheel. There's a contact patch that's frictional. So as this thing is rolling, there's a twisting friction. There's probably little micro collisions with the ground as it's bouncing along also. So there's dissipative contact. And if, as we saw in that video from Cornell, if it's rolling fast enough and you disturb it, it will right itself. And again, it's due to some combination of the dissipation and the pure rolling constraint. An ideal wheel, where it's modeled without having any dissipation, it has this non-holonomic constraint. It has, because of the fore-aft symmetry, as it turns out, in the mass distribution, items like, or devices like this cannot be asymptotically stable. If you disturb it, it will wobble forever at some new heading direction, and but it will the wobble will never die out. The monocycle, or this wheel with crooked masses, has the same non-holonomic rolling constraint. But it has fore-aft asymmetry. It has crooked masses. The question is, can it be stable? There was previous work done on this. The first was done by Carvalho in 1898. Did this massive work on the study of the stability of unicycles, monocycles, and bicycles. He was able to show that with a rigid rider that was tilted backwards with respect to the wheel, could be stable, but there were some errors in the equations that we found, but they only showed up. Only some of those mistakes showed up in the linearized equations, but nevertheless, he found the right conclusion that agreed with the work that we did. There were three other people that worked on this, but the cases they examined were precluded from having stability because of fore-aft symmetry in the mass distribution. So what was the analysis approach for this? Get the nonlinear equations of motion in 3D, linearize about the steady motion in this case, which was vertical constant speed, straight line motion. Look at the eigenvalues of the linearization about that steady motion. Want all the eigenvalues less than the real parts of all the eigenvalues to be less than 0 for asymptotic stability. And the only thing to play with here is adjust the mass distribution to achieve to achieve stability. This is the mathematical model. A simple thin rod is used to model the rider without any real loss in generality. There's a hoop, which is or the wheel, which is the second body. And again, it has all the features that I talked about for the rules that we were playing by. And notice again this frictional guide and support, which is again just to hold the mass in place. It doesn't affect the overall dynamics. So again, just to give you some more details on how we did the modeling, we used one particular set of Euler angles of the 12 that there are: heading angle, lean angle, pitch angle. For those of you that aren't familiar with what non-holonomic means, there's a number of ways to think about it. Mathematically speaking, the dimension of the configuration space is bigger than the dimension of the instantaneous velocity space. What that means is that as you're rolling around without slip, instantaneously you only have 3 degrees of freedom, but compared as opposed to the 5 variables that describe where you are in space, the orientation and the location. So what that means in practice is you need special moves to get around on the plane. So like when you're parking a car, or you have to go through special movements or special motions to get from point A to point B. You can't just slide there. You have to take special steering and backing motions to get to different places on the plane. So there are only 4 mass distribution parameters here. The 4 aft location of the center of mass, the vertical position of the center of mass, and in the inertia matrix, it's just I, which is the moment of inertia for a thin rod, and the angle at which that thin rod sits inside the wheel. So overall, there are 8 parameters, but 6 are the free parameters that you can play with. When you linearize the equations of motion about that steady rolling and vertical rolling, you get 3 equations. The first one is a perturbation to the rolling rate, and it turns out that's just gives you that there's the rolling rate is constant to first order. But here are the important equations that govern stability. It looks like a spring mass damper system where there's a coupling between the bank and heading angles and rates and accelerations. And that's all due to the mass distribution and the steady rolling rate. So you get these possible stabilizing terms. There are 2 coupled equations. So remember, in the beginning, I said, recall this damped sprung inverted pendulum. There you actually had damping and stiffness terms. Here, it's all due to coupling from the non-harmonic rolling constraint and the crooked asymmetric mass distribution fore aft. These are what the 3 matrices look like. All the terms in there are just the radius of the wheel, the fore aft location of the center of mass, and the rolling speed and acceleration due to gravity. And as it turns out, asymptotically stable, steady vertical motion rolling is possible. And even with one very simple case of the thin rod shrinking to a point mass, having the point mass behind the center of mass, the center of the wheel, and having the center of mass or having this point mass above the center of the wheel is enough to guarantee stability in the absence of dissipation and any other kind of features. So this is a full nonlinear simulation depicted here. This is the state of the monocycle in response to a disturbance in the heading and bank rates. And you can see that the heading angle is restored, nearly restored. You end up at some small heading angle that's different from the original direction. The bank angle returns to 0, the bank rate returns to 0, and the heading rate returns to 0 eventually. And the rolling speed ends up just being a little bit bigger, and that's due to the disturbance. When it dies out, the energy from that goes into a faster rolling rate. So with this linearized stability analysis for this system that's uncontrolled, conservative, there's no energy dissipation, simple non-holonomic constraint for rolling, you can get stable, steady motions. Don't know what the basis of attraction is for initial conditions for that stable motion. And again, only 3 features are important to get the stability: the non-holonomic constraint, the crooked mass distribution, and fast enough rolling above a critical speed. So this device joins a very small, exclusive group of conservative, statically unstable, rigid body mechanisms that happen to also be able to have stable, steady motions without control. There aren't many things that can do this. A very special case for this monocycle model is, imagine that the wheel is massless. So it's spinning, but it has no rotational inertia. So there can't be any gyroscopic effects. It turns out that that the gyroscopic effects or the rotational inertia is important for stability for the monocycle. But what this would be equivalent to is a rigid body on a skate. So imagine this skater in this sort of holding herself in this fixed position on a skate. And this is analogous or equivalent to the monocycle with a massless wheel. So that an open question is, what might stabilize a rigid 3D skater? We looked at an asymmetric mass distribution fore aft, so with lateral symmetric mass distribution. But suppose you allowed a full moment of inertia matrix, so it was crooked, mass distribution is crooked in all senses with respect to the plane of the wheel. This is an open question. I think there's work to be done on this. If one could find an answer to this question, it would be a benchmark example because it would be the simplest in this class of systems that we're looking at. Next, let's look at rimless spoked wheels and passive dynamic walkers. We're getting close to the end of time. There's a lot that I wanted to cover here, and I knew it was going to be hard. So there's way more.
Don't worry about time, Mike.
Okay.
You do what you do. Yeah.
Okay. So in any case, so now we're moving from smooth rolling systems to non-smooth systems, where there's smooth motions interrupted by these impulsive collisions or events, collisions with the ground, collisions between at the joints, as these systems move around. So again, here's an outline of the procedure for studying such systems. Again, just like with the monocycle or any of these systems, define a complete mechanical model, material properties, contact mechanics, kinematics, collision mechanics, defining what we mean by a cycle of motion, which is equivalent to the idea of a gait in walking systems, and what the physical dimensions are. Derive the equations of motion between collisions, using Newton's laws of mechanics. Derive a collision law that gets you from just before a collision to just after a collision. The way that Tad McGeer studied the systems and the way that we ended up doing it was the idea of constructing a stride function, a return map, which looks at the state of the system from just before or after a collision to just after the next collision, before or after the next collision. Take the nonlinear equations of motion, integrate them between collisions, have procedures in place to detect collisions, then apply a collision rule. We always would draw to the screen as we were solving the equations to see if things looked right, and then repeat that process. Do all sorts of checks as necessary in the simulation's validity. Is energy conserved when it should be between collisions, and so on? Are we walking above the ground and not below the ground? Do we have our signs right on all of the equations? Then next, search for these fixed points. Fixed points of a map correspond to periodic limit cycle motions overall, which are walking, what we call walking gaits. Then determine the fixed point stability by looking at the the map and its and the Jacobian of the map, the derivative of the return map, so to speak, evaluated at a fixed point. And then, as necessary, do a parameter search to find stable motions using whatever kinds of optimization procedures one can do to accomplish that. Here is a schematic of the procedure, and I'm showing here the case for the 2D rimless wheel, which is confined to move in a plane. Can you see my cursor okay when I'm pointing here?
Yes, we can.
Yeah, I
Okay,
can.
okay, good. So anyway, so here's the rimless wheel just after the ice collision. Then it rotates about this spoke tip here on the ground. It's an inverted pendulum, and then has the ice plus one collision. That's one complete cycle. So we go from just after collision I, use Newton's laws to write the equations of motion, use collision rules, collision mechanics to get a collision rule from just before collision to just after. This is what it looks like in phase space. You have this initial state of the rimless wheel just after a collision. What is the angle theta, which is determined here completely by the angle between the spokes. That never changes, but the angular rate can change, which is theta dot. The trajectory in phase space describes the motion between the collisions, and then there's the state of the system after the next collision. You write a function which takes you from the state of the system just after a collision to the state of the system just after the next. There will be discontinuities in the velocities of the collision. A condition for periodic motion is that the state of the system is the same from just after collision to just after the next collision. So we call that state, we indicate it with an asterisk. Numerically, we use Newton's method to find that. For the 2D rimless wheel, you can do it by hand, find solutions in closed form. The condition for stability of that fixed point, which corresponds to a limit cycle trajectory, is you find the eigenvalues of the Jacobian of the map evaluated at the fixed point, and you want the modulus of that of the greatest eigenvalue to be less than 1, and the system will return to its a stable return to the limit cycle when disturbed from it. So my entire dissertation was based on finding for 3D walking the max eigenvalue, the Jacobian of the stride function evaluated at fixed point to be less than 1. So the number 1 was a very important number for me. What are the features of mechanical walking systems? There are these periods of smooth motions, unstable falling. These smooth motions are disrupted by the foot collisions or joint collisions where velocities change quickly, and there is possibly, if things are working well, support transfer. So that's the catching part. And then after a collision, another phase of smooth motion, and then you repeat that. So fall, catch, and repeat. So in these models, we assumed rigid bodies. Gravity is the only external force due to going down a small slope. For foot contact, we assume the feet or the spoke tips make hard collisions with the ground. Once a foot contacts the ground, it maintains hinged or sticky contact or rolling contact until the next foot collides. Each foot leaves the ground non-impulsively. We assume no torques at the foot contact, no twisting resistance, no tension forces at the foot contact. Again, no activation and control. Left-right symmetry for the rimless wheel, asymmetry for the walking models. And also, to start anyway, no hinge friction in those springs. These are the schematics showing the parameters for the rimless wheel. Again, 312 Euler angles for the orientation. In between collisions, the motion for this is simpler than for the rolling wheel, the rolling disc. It's an inverted rigid body pendulum, so that makes the dynamics easier and the equations easier to derive. It turns out that if you have a big enough slope, and that's all that's necessary, you can have stable periodic motion, stable walking gaits for a rimless wheel. These plots show the state of the system when disturbing it a little bit in the bank angle. Again, the rimless wheel can right itself, and the disturbance dies out in the heading and in the bank. You do end up again at a slightly different heading angle. The pitch angle for the rimless wheel between collisions looks different because it just keeps repeating itself for the pitch angle, but the pitch rate for this inverted rimless wheel in between collisions, you can see it increase, and then at each collision it dies and comes back to the same rolling speed in between collisions. This is a video of from a MATLAB simulation. Believe it or not, this was it took this video using a video camera of the computer screen. So it was before I had this ability to do this on the computer, to save it as a file and so on. Okay, so summarizing wheels. 2D rimless wheel as asymptotically stable fixed points. These fixed point motions become the starting point for 3D, the study of the 3D rimless wheel, and they are fixed points in 3D. The 3D rimless wheel has a one-parameter family of asymptotically stable steady motions. We found that numerically with the full nonlinear equations, and also analytically with an approximate method for large numbers of spokes. Work that I did with a Nindo, with some procedures and approaches that he came up with. Then again, the monocycle, this 3D rolling disc with crooked masses, unlike the rimless wheel, which has dissipative collisions, we assumed no dissipation, just non-holonomic rolling constraints. Again, you get family of steady motions. We were able to do this analytically in closed form and numerically and show agreement. But it needs rolling inertia for stability. That's not a good insight for walking. It didn't because in walking systems, they are notably lacking in fast spinning parts. What else do I want to say about these monocycle? I guess that's it. Okay, so let's go to passive dynamic walking in 3D. So I started with a straight-legged point-foot walker, the simplest model I could come up with. Each leg, though, however, had a center of mass location that you could specify and a full moment of inertia matrix. So that's what we were able to adjust to see if we could find stable walking. 10 parameters in total. Again, following all the same procedures we did for the 2D and 3D rimless wheels for deriving the equations of motion, finding a return map, and so on from step to step. However, the best case after a lot of searching was that I could not find stable, steady walking motions for this model. The best I could find was that the maximum eigenvalue of the Jacobian of the map at steady motions, which we could find, was slightly bigger than 1, slightly unstable. But what it indicated was that it's the parameter optimization discovered tightrope walking. Lateral balance bars are good for stabilization. A low center of mass, but just high enough so that the walking model couldn't stand still is good for stabilization. But I failed. I didn't, in my dissertation work, I could not find stable 3D walking. So in order to show the best failure and my thesis defense, I made a Tinker Toy model to indicate the best that I could find. And the Tinker Toy walker was born. I made this, as you can see, this Tinker Toy walker as something just to hold up in my dissertation and say, this is as close as we could get. Perhaps, we can find stable walking motions, but more work has to be done. But when I was sitting in the lab at like 4 o'clock in the morning, this Tinker Toy model was standing on the table, and I bumped into the table and it started to walk. And over like a couple of days, I was able to get this thing to walk by playing around with the mass distribution and making sure that it still couldn't stand still in any configuration, even with the legs splayed. And it can, by accident, it was able to find through a whole bunch of unquantifiable tinkering, something that was based on a model that wouldn't quite work, but could work in reality. Got a lot of notoriety for this. I just had to show you this picture from Der Spiegel magazine. Somehow we did this work around Christmas time, and it caught on in the popular press because it was Tinker Toys and had to do with understanding walking. So I was proud to end up on the same page with the Spice Girl dolls in Der Spiegel, the German magazine. It also got covered in the New York Times, The Economist, New Scientist magazine, and Nature in their online public press version. So what was the lesson from the Tinker Toy walker? We constructed a device that can balance apparently while walking without any control or fast spinning parts, but it cannot stand still. Why is this? At that point, we still did not know what modeling features were needed to predict that observed stability that we could see in the lab. It's very subtle foot contact. We had little springy, damping kind of strips on the feet. There's clearly hinge friction, which isn't in the model. Rod flexibility, which you can see when it's walking down a slope. There's play in the hinges. It was based only somewhat on modeling. And it could highlight that uncontrolled dynamics may contribute to lateral as well as fore-aft balance. And it was only marginally stable, not very robust. Took a lot of launches to be able to get walking, but to be able to walk as far as it did, it at least had marginal stability. Clearly, it's not very human-like in its mass distribution or other walking features. We did keep working on this. We eventually found on the computer asymptotically stable motions for a model that we started with, which had toroidal feet. But for the case of disc feet of a certain radius, with my colleagues, Katja Mombauer, Mariano Garcia, and my advisor, Andy Rowena, we were able to show that it was plausible that Tinker Toy walker could have stable, steady motions. Not enough to explain exactly why, but at least we were able to show that with our idealized model, that these kinds of motions were possible. So just to summarize here, we wanted to find stable motions for a simple assemblage of rigid bodies and connected by hinges. We were not at this point trying to accurately model the toy in this modeling. final set of modeling or the humans. We did use the Tinker Toys approximate parameters to start the numerical searches with this more complicated model with toroidal and disc feet. As I said, it can explain, if you look at the animations that we made, it had very similar motions to the motions of the walking, the Tinker Toy walker. So qualitatively, it was similar. Again, we don't know what the basins of attractions were. We didn't try to calculate that. We don't know how robust these models can be. We don't know if these stable parameters that we found on the computer are the basis for a device that we could build that would be better than the Tinker Toy walker. And we didn't continue the modeling. We didn't continue the work, so we don't know if more human-like stable passive dynamic designs, free to move in 3 dimensions, that can't stand still, could be made. So that's an open question. The future for work that I still think about. The monocycle work is significant, and it's a benchmark kind of result, but it's still unpublished, so I want to publish that. I'm interested in the rigid figure skater stability. Is it possible to find that case of a device that only has special kinematic constraints, a very special mass distribution with no fast spinning parts and no dissipation, and can it be stable? I'm also interested in other locomotions, animal locomotions for humans and other animals. Cross-country skiing is an interesting kind of locomotion. Ape swinging or brachiation, from swinging from branch to branch, something I've also looked at. As it turns out, over the years, it's not clear to us that the passive dynamic approach and then going to and then evolving to powered controlled walking is the way to go. Control can actually be easier, starting with controlled powered systems. And Andy Ruina talks about this a lot and has thought about it a lot. So that's the end of my talk. I want to thank a bunch of people that I worked with and who helped me a lot on this work. At the Cornell University Human Power Biomechanics and Robotics Lab, the Andy Ruina, my thesis advisor, was the director of. Had a number of students come through while I was there. Anindo Chatterjee helped me a lot with the work. And then there were a number of other students in the lab: John Camp, Mariana Garcia, Larry Goss, Jan Yevmenenko, Steve Collins, Septarsi Haldar. And then there was a visiting student, Martijn Vissa, who's at the Technical University of Delft, and Katja Mombauer, who was also a visiting postdoc in our lab, who helped with the work on 3D passive walkers. Thank you very much again for the invitation and the opportunity to talk to you about this work.